Check it out now, y'all.
nanoHUB-U, online instruction.
This is problem number 1 of week 5. The problem here is to calculate the thermal conductivity of silicon as a function of its length and see how the thermal conductivity varies. So firstly, let me write down the expression for thermal conductivity. So thermal conductivity is just given by a product of the spectral conductance GQ and the length L divided by the area. We write area under quotes here because area can mean different things in different dimensions, but this is just a 3-dimensional problem, so area is just the usual, has the units of length square here. So this is given by L by area times 1 by 2 pi integral over frequencies from 0 to infinity of area times the mode density times the phonon energy h bar omega, and then the transmission function T times the derivative of the Bose-Einstein distribution function, and this is integrated over all frequencies. Now in this problem we use a rudimentary model for the transmission function. So the transmission function is given by the mean free path divided by the mean free path plus the length. And you can see that the area cancels out of this expression as we expect it to be, because we expect that the thermal conductivity is independent of the area of the specific geometry under consideration. And the mode density m3d of omega is just given by a product of the average group velocity and the density of states, and an extra factor of pi. So the average group velocity in 3 dimensions is just Vg over 2, and the density of states under the Debye approximation is given by omega square by 2 pi square Vg cube. So this simplifies to omega square by 4 pi Vg square. So note that Debye approximation is being used here. And once we substitute this expression for the number of modes into the integral over here, and if you also make a change of variable given by x is equal to h bar omega by kBt, the thermal conductivity can be written in the following form. It's given by first the terms that depend on length, and then a set of fundamental constants kb power 4 by 8 pi square Vg square h bar cube, and then there's the temperature dependence which goes as T cube, and then the integral from 0 to the Debye temperature normalized by the temperature T of x power 4 e power x by e power x minus 1 the whole square dx, where x is the non-dimensional frequency as defined over here. And theta d is the Debye temperature of silicon in this case. So now we just need to substitute values for the Debye temperature and evaluate this integral. And we have also been given that there is just one branch that we are considering here. So and the average group velocity of this particular branch is also given as 6,400 meter per second. So the group velocity is given, and the Debye temperature has been given to be 645 Kelvin, and we are calculating the thermal conductivity at a temperature of 300 Kelvin. So we know all these values, and we are also given given value for the mean free path. It's given to be 200 nanometers, and it has been assumed to be independent of frequency. So that's a simplifying assumption that is made in this problem. So once we plug in all these numbers, we get the thermal conductivity to be 146.02 times L by the mean free path plus length. So this shows the length dependence of the thermal conductivity. So clearly as L tends to infinity, the thermal conductivity will just tend to 146.02. So the bulk value is so this prefactor over here is just the bulk value of thermal conductivity. That is the value when L is very large. And if we actually plot this function, it looks something like this. So this is the thermal conductivity as a function of length, and as you can see, as the length increases, the thermal conductivity tends close to the bulk value. So the bulk value is somewhere here. So that is the 146.02 that we calculated, and you can see that for all lengths that are greater than about 15 microns, the thermal conductivity calculated here is very close. It's within 2% of the bulk value. So that's the whole idea. So as we increase the length, the thermal conductivity essentially becomes independent of length, which you can see since the curve flattens out and it approaches the bulk value. And yeah, that's about it for this problem.
All right, we're solving problem 5.2 now. And in this problem, we're asked to calculate the transmission function by the acoustic mismatch method and the diffuse mismatch method in parts A and B, respectively. And then in part C, we want to compare the results to experimental data and kind of pick which one looks better. So part A involves the acoustic mismatch model, and we will take the Debye approximation for all of this problem just to make it a little bit simpler. And we need to start the acoustic mismatch problem by calculating the transmissivity. That's the fraction of the energy that goes from side 1 to side 2. And it has a fairly complicated form that was given in the notes. I'm writing it out here. It involves these terms Z, which are the acoustic impedances. That's the product of mass density and group velocity. And then these angles, these are refraction angles that we'll get to in a moment. So that's our transmissivity. And then we need to find an expression for the refracted angle theta 2. That comes from Snell's law. And that's probably familiar to most people from the study of optics. Here we can use essentially the same principles because we have a linear dispersion, at least approximation here. But these are related to the angles theta 1 and theta 2. Theta 1 is the incident angle. Theta 2 is the refracted angle. Those are related to the group velocities on both sides. So what we need to do here is to integrate this transmissivity over all of the incoming angles. That's theta 1. So if I drew the interface here, it would look like this. I have side 1, side 2. I have some incident, and I draw a normal to it. This is theta 1, and that will be refracted somehow. Let's say that it's refracted like this. This would be theta 2. And I need to integrate over all of these incident angles. And the issue with that is that, as you'll recall, when we defined the number of modes from way back when, a week ago, week 4, we said that we were essentially taking an average of the velocity in the direction of transport. And now we have a transmission that also depends on that angle, the angle with which the carrier is moving. And so we need to define a transmission coefficient, we'll call this TAMM, as sort of the product of the number of modes and the transmission function. So that MT, I want you to think of that as one single entity, and we'll normalize it by the number of modes expression that we had from before, just to keep some consistency. Well, this is going to equal 2 times an integral from 0 to pi over 2. The only reason I'm having that factor of 2 is that I'm using symmetry here. So we're actually integrating over all of these angles from minus pi over 2 to pi over 2, but because the problem is symmetric, we can make it a bit simpler. And so that's going to equal T12 times the sine of theta 1 times the cosine of theta 1 d theta 1. Now that, in this case, you have seen undoubtedly where the cosine term comes from. We had that before when we were averaging velocities. The sine term here comes from the definition of a solid angle. And everything else in this ratio kind of cancels out. But it's not so easy to calculate this. In fact, it's quite difficult, as you might expect. We have two equations where we have to plug the results, the solution for theta 2 into this equation. And there's nothing really that simple, no analytically simple way to do that. And so typically what's done is it's tabulated or put in graphical form. And indeed, that's what we have for this homework problem. We put it into a graphical form. And so now we have these ratios. So this will depend, this transmission function will depend on the ratio of Vg2, the group velocity in 2, to the group velocity in 1. And this is about 0.9 from the values given. And the density in medium 2, density in medium 1, this is about 1.2. We look up the values for this transmission function in the graph that was provided, and we find that the transmission function is about 0.96. And hopefully that's a reasonably intuitive result, because these materials are fairly well matched. Their group velocities are fairly close to each other, and their densities are alike as well. Moving on to part B. Now we want to solve for the diffuse mismatch transmission function, which is sort of the opposite side of the spectrum. The acoustic mismatch assumes that there's a continuity of coherence as the wave travels through, and the diffuse mismatch says everything gets jarbled up at the interface, and then it's spit out on either side according to the number of modes. So we had this before. We talked about this in the lecture. The diffuse mismatch transmission coefficient is equal to the number of modes on the second side divided by the number of modes on the first plus the second side. So it's sort of the fraction of the number of modes on the other side. The more modes on the other side, the more likely it is that the wave will go through. And in this case, I've simplified this problem. We're only looking at a single branch. If we had multiple branches, then we would also allow switching of branches, so mode conversion, sometimes that's called. But since we only have one branch here, these number of modes in the acoustic, or rather in the Debye approximation, is simply, those are proportional to 1 divided by the group velocities in the media, the respective media, squared. And so I can plug in these numbers. And when we go ahead and plug those in, Vg1 in this problem is 6,400 meters per second. Vg2 is 5,600 meters per second. And we find that the diffuse mismatch transmission function is therefore 0.56. All right, now the last thing we have to do, this is part C. The last thing we have to do is to convert this into a thermal boundary resistance or interface resistance. So here, the normalized, this is area normalized interface resistance, will be equal to the inverse of conductance, and we've gone through that enough hopefully by now that at least it looks familiar. This is going to be 1 over 2 pi times the integral of the carrier energy, that's h bar omega, multiplied by the mode density. In this case it's a 3D problem. That will depend on omega potentially, times the transmission coefficient, multiplied by, in this case we have Bose-Einstein statistics, the temperature derivative of that, integrated over all these frequencies. And again, it's an inverse. The integral term there is the conductance, and so the resistance is 1 divided by that. So what we're going to do, since we have transmission functions that do not depend on frequency, we can kind of pull these things out. We will make a change of variables in this. We'll say that x is defined as the carrier energy h bar omega divided by the thermal energy, that's kBT. And we can rearrange some things here. We find that we can express this interface resistance as a collection of terms. There's of course some derivation that goes into this, and we've done most of it. It's just a lot of algebra. And we're going to integrate up to the Debye temperature in silicon, the normalized Debye temperature in silicon. Now, there's a nuance here. You'll notice that I had an upper limit of infinity here before, and really that's a general term. What happens is the number of modes will only go up to the top of the Debye frequency, and thereafter it's 0. And so that's how we switch that limit of integration. The rest of the terms inside the integral can be expressed in terms of x. This comes from some things we've done before in expanding that temperature derivative of the distribution function. And so now this integral itself is fairly easy to evaluate. You can do it numerically. And so certainly if you have low temperatures, as we can assume in this problem, you can still approximate that upper bound as infinity. So we will approximate that as infinity, and when we do that, the integral itself is 4 pi to the 4th over 15. And so what we find ultimately here is that this thermal boundary resistance or interface resistance can be expressed as a group of constants. And we're treating, again, the group velocity in silicon as constant multiplied by our transmission function. We're going to plug in different values for that. And that the t to the minus 3 power comes from the prefactor above. What we find if we apply this at 10 Kelvin, with the acoustic mismatch model, this will equal 4.18 millimeters squared Kelvin per watt. And if we apply the diffuse mismatch model, again at 10 Kelvin, that's the experimental temperature, this becomes 7.18 millimeters squared Kelvin per watt. And the experimental result showed that they had a thermal boundary resistance of 4.5. So I'll put that here. R double prime experimental equals 4.5 millimeters squared Kelvin per watt. And so it looks like the acoustic mismatch model is better for this problem. All right, that's it. All right, we're solving problem 5.3, and in part A, we're asked to calculate the current density for a material with a given work function and electrochemical potential. And so to do this, we use the Richardson-Dushman equation. So this J, this is a three-dimensional material. This equals the electron mass. We're assuming here a free electron metal, multiplied by a number of different constants. I'll just write them out here. This is coming from the course notes. And this Richardson-Dushman equation has a t-squared dependence, and then we multiply that by an exponential term that has the work function in the numerator of the argument and temperature in the denominator. And so this ends up being usually listed as some constant A times the temperature squared times an exponential term minus the work function over the thermal energy, that's kBT. And so we substitute. We have a temperature of 400 Kelvin. We have a work function of 2.36 electron volts, and we know that, and here mu, which we'll use a little bit later, is 5 electron volts. Richardson's constant itself is 1.2 times 10 to the 6th amps per meter squared Kelvin squared. That Kelvin squared comes from the T squared in the equation. And we find, when we do all this substituting, that the current density for this problem is 3.87 times 10 to the minus 19th amps per meter squared. And then part B of this problem asks for the energy at which the energy distribution is a maximum. And we said in the course notes, and this just really comes from looking at the electron energy distribution equation, the maximum happens at, so this is the energy at which the peak spectral emission occurs. That happens at kBT past the barrier height, and this barrier height I'll show in part C. That's the sum of the electrochemical potential, mu, and phi, the work function. And so we just go ahead and plug in these numbers, and this turns out to be 7.39 electron volts. And then we are lastly asked to show qualitatively the transmission function and the electron energy distribution. And so I'll draw that here. So this is the energy distribution. That's the derivative of the current density with respect to energy. And we're drawing this as a function of energy. And we will say that, let's say that this point is the sum of the electrochemical potential and the work function. And then on the parallel scale, we'll write the transmission function. That's over here. I want to start with the transmission function. What we found in class is that it's a fairly simple relationship. It's a step function, but it's weighting over all of the different directions. So the transmission function right at the work function energy, that starts at 0 and then it ramps up. And we'll draw a fairly narrow energy range here. So it sort of looks kind of linear, and then it starts to tail off above that, but it can at least be approximated as linear, and near the work function, I should say. And the electron energy distribution, so let's just draw this kind of barrier level. That's where the work function is. The electron energy distribution, because the transmission function starts at 0, the energy distribution will also start at 0, and then it will come up pretty quickly to a peak, and then it tails off something like this. And this is really the tail. The tail that I just drew is the tail of the Fermi-Dirac distribution, more or less. It's weighted by that transmission function. And from part B, this distance between the peak of the electron energy distribution and the level of the work function, that's kBt. All right, that's it for this problem.
In the fourth problem, we are going to explore the effect of nanostructuring on the thermal conductivity of a material. Now, it's been shown experimentally that nanostructuring leads to confinement in the dimension of a material, and that results in drastic conduction in the thermal conductivity. So in this particular problem, we are going to calculate the thermal conductivity of 3 different confined nanostructures of silicon. So the schematic of these 3 nanostructures are drawn on the screen in front of you. The first one is a nanowire sort of a structure which has confinement, the values of which is 10 nanometers by 10 nanometers. The second structure is a thin film sort of a structure which is 100 nanometers wide and 25 nanometers thick. And the third one is again a nanowire sort of a structure which is 400 nanometers thick and 100 nanometers wide. So you can see that there is confinement, nanoscale confinement in these structures, and we'll show through our calculations that this results in a drastic reduction of the thermal conductivity of silicon. So let me start off by writing the general expression for thermal conductivity, something which has been worked upon in the first and the second problem. So kappa is given as 1 upon 2 pi integral 0 to infinity lambda of omega, which is the frequency dependent mean free path, multiplied by 3-dimensional number of modes. So this is a 3-dimensional material which has been confined along certain dimensions, multiplied by h bar omega. This is multiplied by the temperature derivative of the Bose-Einstein distribution and d omega. So in this problem, we will make the Debye approximation, which is essentially the linear dispersion of the acoustic branch. And upon invoking the Debye approximation, which results in a certain expression for the density of states, we can simplify this expression as 1 upon 2 by integral 0 to omega d Vg upon tau inverse omega pi Vg upon 2 omega square 2 pi square Vg cube h bar omega partial derivative of the Bose-Einstein distribution d omega. So in this expression, we note there are 2 constants for which we need to know the value to calculate the integral. The first is Vg, which is the group velocity. So in this problem, we will average the group velocity of silicon over the longitudinal and the transverse acoustic modes. And upon averaging, the value of the group velocity comes out to be 5200 meters per second. The second sort of constant that you see here, or the value which is required to solve this integral, is omega d, which is the Debye frequency, and that in case of silicon is 52.9 terahertz. So we know the value of the Debye frequency, we know the value of group velocity. Omega is the variable here to be integrated. Now the only other sort of constant which we need to find the value of is tau inverse, and this is the scattering rate, and this is where you'll see the effect of confinement. Now in our problem, the phonon scattering rate will be given as the sum of 3 different scattering processes, which in this case is scattering due to impurities, which is given by the subscript I, scattering due to the boundaries or the confinement, which is given by the subscript B, and scattering due to the Umkulap phonon-phonon interaction processes, which is given by this. Now, the impurity scattering in this case, we employ a Clemens model for a Rayleigh type of impurity scattering, which is essentially given as A omega raised to 4. The boundary scattering rate is given as Vg upon root L1 L2, and the Umklapp scattering rate is given as Bt omega square e raised to minus c upon t. A, B, and C are can be called as scattering constants in this case, the values of which are given in the question, but I'll still write it down here. So A is 1.32 into 10 power minus 45 second cube, B is 1.73 into 10 power minus 19 second upon Kelvin, and C is 137.39 Kelvin. So I want you to pay attention to the boundary scattering term here, and you can see that this is where the effect of confinement is noticed. So the denominator of the boundary scattering rate contains L1, L2, and the L1, L2 values are given from these schematics. So in the first nanowire sort of a structure, we have L1 equals to 10 nanometers, L2 equal to 10 nanometers. In the second case, we have L1 equals to 25 nanometers, L2 equals to 100 nanometers, so on and so forth. So upon substituting all these values in the boundary scattering term, and upon further substitution of the scattering constants, we can find the effective, or rather the total scattering rate in the system, which can be put back into this integral to find out the value of thermal conductivity. Now, this integral has been solved in the first and the second homework problem. It is not a very direct integral to solve, and the numerical integration is made easy by the following substitution: x equals to h bar omega upon kbt. For further mathematical intricacies involved with this substitution, I refer you back to the first and the second homework solution. But upon calculation of this integral, we find the following thermal conductivity values for the three nanostructures which were described above. So this is the thermal conductivity of the first nanostructure, this is for the second nanostructure, and this is for the third nanostructure. And we see the values are 3.5 watt per meter Kelvin, 12.2 watt per meter Kelvin, and 24.6 watt per meter Kelvin. Of course, all these values are at 300 Kelvin. So this entire calculation was done at 300 Kelvin, something that I should have mentioned at the start. So we can see the effect of confinement on the thermal conductivity of silicon. Just for reference, I'll give you the thermal conductivity of bulk silicon at 300 Kelvin. It's approximately 150 watt per meter Kelvin. So you can see almost an order of magnitude reduction in thermal conductivity because of nanostructuring. In fact, for the first nanostructure, the value goes down to almost around 1 watt per meter Kelvin, which is essentially the amorphous limit of thermal conductivity. So you can see that nanostructuring results in drastic reduction in the thermal conductivity, and this particular fact has been exploited by scientists in designing thermoelectric materials in particular. Thank you. As part B of the fourth homework problem, I'll briefly describe to you a CDF tool which lets you calculate the thermal conductivity of silicon and germanium nanostructures. We saw from part A of the fourth problem that nanostructuring results in a drastic reduction of the thermal conductivity of a material, and this tool lets you calculate what is the exact thermal conductivity given the extent of nanostructuring in the system at different temperatures. So the graph that you see on your screen plots the thermal conductivity as a function of temperature. The temperature goes from 0 Kelvin to 600 Kelvin, and this tool lets you find the thermal conductivity of silicon and germanium nanostructures. So the two buttons on the top lets you select the material. So if I click on silicon, this will give me the thermal conductivity of silicon, and if I click on germanium, it will give me the thermal conductivity of germanium. Now, the extent of nanostructuring in the system is is defined by the boundary size. This boundary size is the root L1, L2 factor that we saw for the boundary scattering rate in part A of the problem. So this tool lets you change that. We can go to a boundary size as low as 20 nanometers in this problem to something as high as 200 nanometers in the system. So the slider that you see next to boundary size lets you change the boundary size of the system, and the play button lets you dynamically change the boundary size and see how the thermal conductivity as a function of temperature evolves. Now we'll make a few observations from the graph here. The first observation is that near about 0 Kelvin, the thermal conductivity follows a T-cube dependence on temperature. Now this T-cube dependence on temperature comes from the T-cube dependence of specific heat on temperature at low temperatures. So this T-cube dependence is a result of the T-cube dependence of specific heat in a three-dimensional material. You also see that as you increase the temperature and as you go around the Debye temperature, which in case of silicon is around 500 Kelvin. So near about Debye temperature, the thermal conductivity starts reducing. The reason for that is that at high temperatures, Umklapp scattering dominates the scattering process and it suppresses the thermal conductivity. The final thing that you would want to notice or rather infer from this particular tool is that as we decrease the boundary size and increase the extent of nanostructuring in the system, the thermal conductivity gets suppressed. And this again is a consequence of what we saw in part A of the problem, that by reducing the boundary size and by increasing the extent of nanostructuring, we are essentially increasing the rate of boundary scattering, and that results in reduced thermal conductivity. Thank you.